Hi, thank you for joining a webinar today. Today's topic is Introduction to Bioconjugation. This will be presented by my colleague, Dr. Craig Powell. He is the Director of Technical Services at Vector Labs. Today's webinar will be about SoluLINK bioconjugation chemistry and its applications. During the 1 hour presentation, we will have a quick FAQ session at the end. Please submit any questions you may have using the chat function to webinar site. I now introduce you, Dr. Craig Powell. Over to you, Craig.
Thanks very much, Byron. And hello to everyone joining us for today's webinar. You know, some listeners may be familiar with our previous webinars or webinar series that focused on applications such as immunohistochemistry and immunofluorescence. Now, as Byron mentioned, today's webinar is on the topic of bioconjugation, which is a little different from our previous webinars, though it's not unrelated, as you'll soon see once we get into the presentation. All right, so here's a quick overview of what we'll be discussing today. We'll look at what is bioconjugation. We'll look at a bit of a definition on that. We'll look at some common examples of bioconjugation, some of the nomenclature and phrases that are used. We'll dip our toe a little bit in some organic chemistry. Then we'll pivot over to look at some really interesting case studies on how bioconjugation is being used to push the frontiers of both medicine and science. Hopefully that might pique some interest for some of you. Then we'll look at the actual SoluLINK chemistry itself, the bioconjugation technology that's incorporated in those products. Then we'll have a look at what the product portfolio is, focusing on some of the kit formats, and I'll mention why we're focusing on that a little later on. And then tips and tricks or do's and don'ts for bioconjugation, some tools and resources that we can make available for you. And then, as Byron mentioned at the end, we'll have some time for a little bit of a Q&A. All right, so let's dig right into it here. What is bioconjugation? And the image I've got here on the left-hand side is probably the easiest one to talk from or visualize at your end. So I've got a molecule over here, a biomolecule that looks suspiciously like an antibody, and you want to conjugate this squiggly line to it. Let's just call this squiggly material peroxidase or horseradish peroxidase. And I'm going to use this example throughout the presentation because it'll be easier just to stick with the one example to try and convey some of these concepts about bioconjugation. So again, we've got our biomolecule, the antibody here. We want to attach peroxidase to it, and that's basically what we do using chemistry to generate a bioconjugate. And this is in fact then a peroxidase conjugated antibody. And this could be a primary or a secondary antibody, for example. So bioconjugation is the chemical linking of two molecules to form a single unit or a hybrid. But since this is bioconjugation, of course, at least one of those molecules in this union or hybrid, you know, would be a biomolecule such as an antibody, a peptide, a protein, or indeed an oligonucleotide. Now, one thing that's very important is the conjugate retains the activity of each of the components. In the example that I've got over here, the antibody, of course, you want that to still bind to its target antigen, and you want this enzyme, the example we're using here, peroxidase, to still be reactive with a subsequent chromogen or substrate that you might apply in a given application. However, another important point is when you do put these two together, you get an additional functionality that you don't get with either molecule alone. So this is the nuts and bolts of bioconjugation. And some of you might be thinking, hey, that sounds a little familiar. And so, yeah, indeed it is. Some of you are probably using bioconjugates in the lab on a daily basis. And on the left-hand side here, I've got an example of a fluorophore conjugated antibody. Indeed, this could be a primary antibody. It could be a secondary antibody, such as an anti-mouse, an anti-rabbit, something like that, where you would have a fluorophore, could be a fluorescein. your favorite dye on there, an Alexa, a dialite, whatever it might be. Indeed, you could swap out the word fluorophore for something like an enzyme, such as the example we just gave on the previous slide. Indeed, for a secondary antibody or even a primary, that could also be biotin or digoxygenin. And we'll be talking about some of those examples a little later on. So hopefully this sort of allays some fears for you about bioconjugation, what it is. And in fact, you are probably using bioconjugates in the lab routinely or almost on a daily basis. Another example on the right-hand side I've got here is an agarose-bound lectin. This could be certainly an agarose-bound antibody as well. But these are agarose beads conjugated with, say, this glycoprotein or lectin, whatever it might be, and then applied in a column format for isolation or capture of whatever it might be. So that's another example of bioconjugation whereby that entity, whether it be an antibody or glycoprotein, is bound to that matrice, these beads in the example I've got here, and then utilized as a tool to extract or capture or isolate a given target antigen or protein, for example, of choice. All right, so now perhaps what I should put up here, or what I should have put up here, is a little warning flag saying organic chemistry ahead. So just bear with me over these next couple of slides and don't be too concerned about some of these structures. I'm going to walk you through these, but after these couple of slides, we'll get into some of the case studies. But I feel it's very important, particularly with an introduction to bioconjugation, to become familiar with some of the nomenclature or phrases that are used out there. Otherwise, if you're unclear on that, then you don't get the full appreciation of what we're talking about. So here are a couple of commonly used names or phrases when we're talking about bioconjugation. And one of them is a functional group. And this is part of a molecule that reacts with the reactive group to form a bond. And the example I've got here again is our antibody. And we've got an amine group here. And usually on antibodies, the idea is to target primary amine groups. There's a lot of them usually through lysines that are present. And it's very easy to use this functional group to then attach other molecules, or linkers, I should say, to the antibody. And I've got an example over here. Here's the linker, this one over here. And those of you who may be familiar with some organic chemistry or perhaps have done some bioconjugation before may identify this molecule as biotin NHS. And basically, just to walk you through it, this is the biotin component here. This is the part that will be accessible for an avidin or a streptavidin subsequent detection conjugate, or indeed an anti-biotin antibody. And then the reactive group over here, this particular group, binds to this functional group linking chemistry. And this is part of the link. The reactive group is part of the link that reacts with this functional group on the molecule to form a bond. Now, so we've just discussed what a functional group is. That's part of the molecule. The reactive group reacts with that functional group, and it's part of the linker. Another part of the linker here is this spacer arm, which separates, or joins, I should say, these two ends of the linker. Now, spacer arms come in a lot of different flavors, I will say, and we'll touch on that a little later on. But basically, a spacer arm, as you can see, separates the reactive group from the business end, the biotin end in this case, of that linker to give it accessibility for subsequent binding by an antibiotin or a streptavidin or avidin molecule. All right, so just become familiar with some of these terms: functional group, reactive group, and spacer arm as we go through the presentation. All right, so here is another couple of terms you may encounter when you look at some of the options for bioconjugation. One here is termed a homobifunctional linker, this particular phrase up here. Another phrase is a heterobifunctional linker. And the example I've got for a homobifunctional linker is actually glutaraldehyde. And many of our listeners out there might be familiar with using aldehyde-based fixatives for tissue or cell staining for subsequent immunohistochemistry or immunofluorescence. And indeed, this is a great example of their action or function in that they do cross-link proteins. And if you look at glutaraldehyde here, it has on either end these actual aldehyde groups. And you can imagine if you do apply glutaraldehyde with an antibody, it would react with the amine groups. You would get an antibody binding here. And similarly, you get an antibody binding here. So these homobifunctional linkers have the same reactive group on either end of the molecule. You can imagine if an antibody was bound here and you had another glutaraldehyde, you get another antibody, and of course the linkage would go on. So homobifunctional linkers limit what you can do a little bit with the bioconjugate afterwards. And indeed, the example I've given here, you'd simply just get a big ball or polymer of antibody, which may be useful in some applications, but certainly not for more specific applications. So usually investigators use something called a heterobifunctional linker, which is different from a homobifunctional linker in that it has different groups at either end of the linker. The example here is a sulfo-NHS ester. This reacts with the mean functional groups. You can remember on a previous slide, we were talking about a functional group on an antibody. So this would bind, this end here would bind to the antibody, and then it has a different end over here, this maleimide, that reacts with these thiol or sulfhydryl functional groups of a different molecule. So you can certainly then utilize this, and this is a molecule called sulfo-SMCC. You can certainly look at that. It's a very popular molecule for conjugating to antibodies and other components as well. All right, so this is pretty much the extent of the biochemistry. We'll be talking about organic chemistry. Now we'll look though at some of the other selections or choices that are commonly used for binding or bioconjugating proteins.